Alright, hey guys, my name is Brittany and welcome back to Probability and Statistics. Thank you so much for tuning into another statistics video. Today we're going to talk all about conditional probability and Bayes theorem. Firstly, what is conditional probability? So it's the probability of an event occurring under a known condition or limitation. And the key word here is given. So we can express this saying the probability of B given A, for example. And this means that we're trying to find the probability of B, but only within the confined sample space of A. And so our sample space is constricted now to the scope of A. So we can also express conditional probability written this way, saying the probability of B given A is equal to the probability of the intersection of A and B all over the probability of A. And we can rewrite this a number of ways, for example, solving for the intersection, saying that the probability of the intersection of A and B equals the probability of A times probability of B given A. And if we break down our numerator and denominator in this equation, we can say that this is equal to the probability of the event occurring all over the probability of the total sample space. In this case, which our sample space is just confined to A. We want to visualize this. Let's just say that this box is our sample space. Let's just say we have a subset of A, a subset of B, and that everything else within the sample space we can denote as a subset of C. So if we want to find the probability of A given B, we'll look first at the sample space of B, which will be this section here, and we'll ask ourselves, where does A occur? So we'll look within B, find that A occurs within B here. Let's just shade this in. And let's also note that the probability of A naught given B is the complement of the probability of A given B. And so let's just redraw our sample space of only B. If we want to say that these two are complements, then we'll say that the probability of A within the sample space of B is just this shaded region here, and that the complement of the probability of A within the sample space of B would be everything else that's not shaded. So this will be the probability of A naught within the sample space of B, or in other words, given B. And so just to break this down even further, we can say that the probability of A naught is the complement of the probability of A, which we know from earlier in our set theory videos. And we can also say that within the confined sample space of B, the probability of A naught given B is the complement of the probability of A given B. And this is just extension of the previous statement. So let's run through a quick example of this. Let's say that we have this given chart where we sampled a number of kids and adults and asked them if they prefer French toast or pancakes. And let's say that we want to figure out what's the probability that we just surveyed a kid, given that we know for a fact we surveyed someone who prefers pancakes. If we use our defined equation from earlier, we know that the probability that we're surveying a kid, given that we know that they like pancakes, is equal to the intersection of the probability of K and P all over the total probability of our sample space of people liking pancakes. And so if we break this down, our numerator, we can find the intersection. So we'll have 62 over 250. And for our denominator, the total number of people that prefer pancakes is 103. Take that over 250, which is the total number of people that we surveyed, and just work this out, you'll get 62 over 103. And let's also take note here that both our numerator and our denominator are probabilities themselves, so they won't be greater than 100% or 1. Alright, let's move on and talk about the total probability in the scope of Bayes theorem and conditionals. So we can say that the total probability of B is the sum of the probabilities that B will occur, given that event E has occurred. For some event B is a unique possible outcome of the mutually exclusive events E sub 1, E sub 2, all the way to E sub n. And so if we want to visualize this, let's just say that we have some n number of events where B is a possible event. So I'll just write out each event here, all the way to event n. And for each event, we have some number of possible outcomes. Let's just call them A, B, C, and D. And for each possible outcome, A, B, C, and D, they each have a slightly different probability of occurring. For example, 10%, 15%, 30%, 45%. And all of these will sum to a total probability of 100%. So for example, within event 1, each possible outcome, A, B, C, and D, will comprise the total probability of 100%. And we'll do this for each event, and each outcome within each event will have a slightly different probability of occurring, as well as overall, all of the events in total have a total probability of 100% occurring, but each event might have a slightly different probability of occurring. For example, event 1 might have a probability of 25%, whereas event 3 might only have a 2% chance of occurring. So let's take into account a couple of key facts here. Event B is a possible outcome for every event E, and we can say that the probability of B for each event may differ, as well as the probability of each event E may also differ. So if we want to find what's the total probability of B occurring, we'll have to take into account the probability of B occurring within each event, as well as the overall likelihood of each event occurring. Alright, so we can break this down into finding the total probability of B is equal to the probability of the union between B and every possible event, E sub 1, E sub 2, all the way to E sub n. And knowing from our conditionals equation earlier, we can rewrite this in saying that the probability of, for example, the component probability of B with the intersection of E sub 1, and break that down, rewrite it using our conditional definition as the probability of B given E sub 1 times the total probability of E sub 1 occurring. So we can break this down for each component to find the total probability of B occurring. Alright, now let's move on and talk about Bayes' theorem in terms of reverse conditionals. So this is where we want to find the conditional probability when we're given or when we know the reverse conditional probability. Thus, if we know the probability of A given B, we can solve for the probability of B given A. And we can express this written as the probability of A given B is equal to what we know as the reverse, which is the probability of B given A, multiplied by the probability of A, all over the total probability, or our sample space, of the probability of B occurring. And let's recall what we just talked about with total probability. If E sub 1, E sub 2, all the way to E sub n, all of these events, if they are mutually exclusive, then we can say that the probability of E sub 1 given some event B is equal to, if we know the reverse condition, we can say probability of B given E sub 1 times the probability of that event occurring, all over, again, the total probability of event B occurring. So the probability of B given event 1 times the probability of event 1 plus the probability of B given event 2 times the probability of event 2. We can do this for every event all the way to E sub n for n number of events that we have, and find the total probability of B occurring within each of these events. And so let's take note of just a couple key characteristics when we're writing the probability of a reverse condition. Firstly, let's take into account that each of our events are mutually exclusive. That means that, just to check our work, if we take the probability of each event occurring in our denominator, that should equal 100% or 1 when we sum them all together. Additionally, if we take the numerator of our equation and if we compare it to the first component of our denominator, they should be the same value. Just another quick way to check your work. And just a last way to check your work, we can say that the probability that an event occurs is our numerator, and that our denominator would be equal to the probability of the event B occurring. Alright, so let's run through a quick example of this. Let's say that we're surveying soccer players and we find that 60% of them also follow professional leagues. Of those who follow professionals, we know that 80% have seen a live match in a stadium within the last year. Of those who don't follow professional leagues, only 10% of them saw a live match last year. So let's find the probability that we survey someone who closely follows a professional league if we know for a fact that they've seen a live match last year. So there's a lot of numbers and a lot of different conditionals going on, but let's break this down. First of all, what are we finding? Well, we're finding the probability that a person follows the professional leagues given that they've seen a match live within the last year. So let's say that our event A is that the person follows the professional leagues, and that event B is that that person has seen a live match within the last year. Secondly, let's write down just what we know from reading this problem. First of all, we know that our sample space is all the soccer players that we surveyed, and that's 100%. And we also know from the first sentence that 60% of the soccer players follow professional leagues. So the probability of A would be equal to 60%. From there, we can solve for the complement of the probability of A. We can say that the probability of A is equal to 100 minus 60%, which is equal to 40%, which represents the people who don't follow professional leagues. From the second sentence, we know that of those who follow professionals, 80% have seen a live match. So we can break this down into saying the probability of B given A, or the probability that they've seen a live match, given that they follow professionals, is equal to 80%. Therefore, we also know that the probability of B not given A is the complement of the probability of B given A. Therefore, 100% minus 80% is equal to 20%, which is our probability for the complement. And in the third sentence of our problem statement, we also can figure out the probability of B given A not. In other words, the probability that a person has seen a live match given that they don't follow professional soccer. And that would just be equal to 10%. And from knowing that, we can find the complement of that probability statement, which would be 100% minus 10%, which is equal to 90%. And that would be the probability of a person who has not seen a live match, given that they don't follow professional leagues. Alright, so these are all the statements that we know. So thirdly, let's ask ourselves, can we use Bayes' theorem? Well, do we know the reverse conditional probability? Let's check. What are we trying to find? We're trying to find the probability that a person follows soccer given that they've seen a live match within the last year. So the probability of A given B. So the reverse conditional would be the probability of B given A. So let's look at our known statements, and we see that we do know the probability of B given A. So we do know the reverse conditional, so we can use Bayes. So fourthly, let's just solve the problem using our equation for Bayes' theorem. So the probability of A given B is equal to the probability of B given A times the probability of A, which is the probability of the event occurring, all over the total probability of the sample space of B. So that'll be the probability of B given A times the probability of A, plus the probability of B given A naught times the probability of A naught, or the complement of A. So let's plug in the values that we know, and we'll solve out to get some number less than 100%. And just to double check our work, let's make sure that our probabilities of each mutually exclusive event occurring will sum to 100% or 1 when we add them together. So that's true. Let's make sure that our numerator is the same value as the first component of our denominator. That's also true. And let's also make sure that we're solving for the total probability of the confined sample space of just B in our denominator. And we know this because we're given B in the question that we're trying to find, the probability of A given B. Therefore, our denominator will only be the total probability of just the sample space of B. Alright, and that's pretty much all for today. Today we went over conditional probability as well as Bayes' theorem when we know reverse conditionals. And if you have any further questions, just leave them down in the comments below and I'll be sure to get back to you. Thank you so much for tuning into another video, and I'll see you next time.